Okay, so we're gonna do a few more examples of Maclaurin and Taylor polynomials. These all involve finite length expressions. So all the problems are similar. They give you a function. They ask you to have so many terms of the series. And for the Maclaurin series, you center your polynomial around x equals 0, and for the Taylor series, you center it around the whatever x value, x equals c. So I don't think I need to do both of these because I've already done something like it already. So I'll just pick the first one here. So here's your function, and they want n equals 4 terms. So we're going to need probably at least 4 derivatives. We did this the other day with e to the x. The only difference is when you take the derivative of e to the 2x, you get 2e to the 2x. And if you take the second derivative, you get 4e to the 2x. If you take the third derivative, you get 8e to the 2x. And if you take the fourth derivative, you get 16e to the 2x. So every time you take a derivative, you get an extra factor of 2 because of the chain rule. And then you evaluate the function at whatever appropriate value. For the Maclaurin series, it's 0. So you get e to the 0, which is 1. For the first derivative, you'll get 2e to the 0, which is 2. For the second derivative, you get 4e to the 0, which is 4. And you can figure out what the other ones are going to be here. So 8, 16. So those are the coefficients we use in the Maclaurin series. If you remember yesterday, the Maclaurin series is you take each one of those derivatives evaluated at x equals 0 and multiply it by the appropriate x to the power divided by that power factorial. So the final part, you just plug it into the equation. So we can say the polynomial that approximates this function is going to be equal to 1 plus 2x plus 4x squared over 2 factorial plus 8x cubed over 3 factorial. That's probably as much as I need to write. I'll do one more term. 16x to the 4th over 4 factorial. So if I plot e to the 2x and I plot the first 4 terms of this series, let's see what they look like. So instead of e to the x, we have e to the 2x. And we have 1 plus 2x plus 4x squared divided by 2 factorial plus 8x squared, and that should be 2 factorial, not x factorial. 8x squared divided by, I did it again here. What am I doing here? 2 factorial. 4x squared divided by 2 factorial. Okay. 8x squared divided by 3 factorial plus 16x squared divided by x cubed divided by 3 factorial. Okay, so there we go. So you can see that's what it looks like. So it's in this case, you can see it doesn't quite work. It's not quite as accurate with so many terms. I remember when we did it the other day with about 5 terms of e to the x, that it matched up pretty good as far as the curve. And it's matched, I mean, ultimately it'll be exact if you take an infinite number of terms, but in this case, it's going to take more terms to get the same level of accuracy between the polynomial and the function. I don't think I made a mistake putting it in. Let me just check. 1 plus 2x plus 4x squared. Oh, there it is. Oh, so maybe it does do better. Yeah, I was like, yeah. Oh, is that what it did? Oh, okay. Yeah. Okay. Apparently, if you do it wrong, it doesn't work either. So let's try that. Thank you. X to the fourth over 4 factorial. Yeah. I've never done this one, so I made a mistake there in terms of actually my conclusion was, so that actually doesn't, it looks pretty good. So ignore what I just said. It could have been true, but apparently it's not. Okay. So that's the Maclaurin polynomial, and then let's do this one, which is a Taylor polynomial. So we're doing the square root of x, and one reason you may choose to center it around not x equals 0 is because at x equals, to the left of x equals 0, it's undefined. So it's not going to do a very good job if you center it around 0. So that's there's practical considerations sometimes. It's like with the natural log. If you look at the sheet that I handed out, the natural log expansion is around x equals 1, not x equals 0, because the natural log of 0 is negative infinity, which wouldn't be too good. So, but we do the same basic kind of thing here. We take the derivatives, and I'm just going to leave it in exponential form. I mean fractional exponential. So when you take the derivative of that, you'll get 1/2 x to the minus 1/2 power. And if you take, that's the first derivative, take the second derivative, you get negative 1/4 x to the minus 3/2 power. So negative half times positive half is negative quarter. And then the third derivative is going to be equal to positive 3/8 x to the minus 5/2. And then next one will be 15/16. So negative 15/16. All I'm doing is taking negative 5/2 times 3/8. So 5 times 3 is 15, 2 times 8 is 16. Then you get x to the minus 7/2. That's the fourth derivative. Another reason for choosing 1 here is that it makes it easy to evaluate these derivatives, because 1 to any power is 1. So in the first case, you get so f of 1 is going to be the square root of 1, which is 1, and f prime of 1 is going to be 1/2, because 1 to the negative 1/2 is 1. And the second derivative is going to be negative 1/4, and the third derivative is going to be positive 3/8, and the fourth derivative is going to be negative 15/16. So in this case, we get an alternating series instead of a non-alternating series. So the actual polynomial is 1 plus 1/2 times x minus 1. So instead of multiplying just by x, we take x minus whatever number this is centered around. So when we put in x equals 1, we'll get, this goes to 0. Because we know the square root of 1 is exactly 1. So all the higher order terms should drop out when x equals 1. Okay, then you have minus 1/4 times x minus 1 squared plus 3/8 times x minus 1 cubed minus 15/16 x minus 1 to the 4th power. So I did more than I needed to again, just because it's not that hard to do an extra term or two. So again, let's look at how well that does. Obviously, this is going to have a domain that's different than this one, because you can't have a negative square root, but hopefully on the positive side, it will match up pretty good. So let's see what we get. So we're going to have square root of x. And let me move this over. I guess it's not, hold on just a second. Just move this over a little bit so I can see my polynomial. So we get 1 plus 1/2 times x minus 1. What we can do is let's just add a term at a time and see what it looks like. So that's the linear approximation. So it's tangent to the curve at x equals 1. So the slope and the value of the function match up. Okay, let's add the next term. Minus 1/4 times x minus 1 squared. Okay, so that's our second order polynomial approximation. Then we have the third term, which is going to be 3/8 times x minus 1 cubed. So that's that. Actually, did I make a mistake? Because that doesn't look right way. Well, maybe it is. Let's see what happens when I add another term. Probably right around x equals 1, it's looking better. Minus 15/16 times x minus 1 to the 4th power. Yeah, so it is getting better, as you can see, around x equals 1. So there's your homework for section 7. I think most of the useful infinite series are either Maclaurin or Taylor polynomials. Okay, so I decided last night I was going to look at last night or yesterday afternoon, I decided to read a little bit on gamma functions, which was kind of interesting. I mean, I didn't read a lot about it, but one thing is it uses integration by parts. I thought that was, it uses integration by parts as well as improper integrals where you integrate from 0 to infinity. And they also use that to solve that. Like they had gamma of 1 and gamma of 2, and they used, I guess they used the same kind of deal we used when we did integration by parts for e to the x times the sine of x. You had to, used integration by parts twice, and then the term that left over was the same as the one that was initially there or something. And so some of the stuff that we've learned you actually can use to try to at least start to understand it. First time I read it, I'm like, what? And the second time I looked at it, I'm like, oh, I'm getting it slowly. But it then starts talking about complex things, and it'll take it. I'd have to read it more than once to figure it out. Because then it said it's like a beta function. I said, oh, I need to read about beta functions too. Have you read about beta functions? No, yeah, okay. It's like, here's beta function something, some hyperlink. Okay, section 8. So we got 3 more sections in chapter 9. And we're going to go until we run out of time. I mean, I'm not going to try to rush to cover chapter 10. If we'll get, like I said, we'll cover this in as much detail as I think we need to. We'll definitely finish chapter 9. I'd rather understand chapter 9 than try to zip through it too much. So what we're going to talk about is power series and the convergence of power series. So the definition of power series is, if x is a variable, then an infinite series of the form, the summation from n equals 0 to infinity of a sub n times x to the n is equal to a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x cubed plus dot 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 a sub n times x to the n plus dot 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 dot. So you establish the pattern. You say the pattern continues. You write out an expression that represents what's going on for any value of n, starting in this case from 0. It doesn't always have to start from 0, but usually starts from 0 or 1. And then dot, 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 that means just keeps going on forever. So that's how you know it's an infinite series. If I just did this, it would be a finite series, but with the extra dots on there. And what we've been, the Maclaurin series and the power series are, the Taylor series are examples of, well, I guess Maclaurin more so, because there you just multiply by x raised to a power. Those are examples of, well, finite power series, I guess. A power series, by definition, is infinite, but if you look back at the one we just did for the square root of x, it was the polynomial approximating the square root of x was 1 plus 1/2 times, well, that was, we don't want to use that one because that was a Taylor series. The one before that was, the function was e to the 2x, and that was equal to 1 plus 2x plus 4x squared over 2 factorial plus 8x cubed over 3 factorial. Was a factorial in there? Yeah, I can't even remember. Was there yeah, that was a factorial. So in this case, this is, if I continue this on forever, that would be an example of a power series. You know, a sub 0 would be equal to 1, and a sub 1 be equal to 2, and a sub 3 would be equal to 4 over 2 factorial, and a sub 4 would be equal to 8 over 3 factorial. And I think you could represent a sub n as something like probably n plus 1 divided by, now, what would it be? These are raised to the power, so it's probably going to be 2 raised to the n power divided by n factorial, right? So when n equals 0, you get 2 to the 0, which is 1, over 0 factorial, which is 1. When n equals 1, you get 2 to the first power, which is 2. 1 factorial is 1. When n equals 2, sorry, it should be a sub 2. When a equals 2, you get 2 squared over 2 factorial. So that's the nth term representation for what we did. But in general, a power series, no matter how you derive it, I guess, as long as it takes on this form, and a lot of times a sub n involves a factorial. Well, actually, okay, more generally, so I forgot about this. One year to the next, I forget stuff. But so I guess you can have a Taylor series, I guess, works out as well. It's called a power series centered at C, where C is some constant. So this Taylor series is centered at 0. This Taylor series, this infinite series is, this infinite series, or the power series, is centered at x equals 0. You can generalize to center at some other value. So that's, you could use a Taylor expansion to come up with the power series that has x minus c raised to some power. Yeah, I didn't think there was any limitation, but I forgot that I hadn't talked about that. So what we're going to do is we are going to talk about two things. One's called the radius and interval of convergence. So the radius of what you'll find is that the function's centered around some value. So e to the 2x that we did earlier was centered around x equals 0. The square root of x was centered around x equals 1. So the convergence tests are centered around some value of x. And then in the worst case scenario, the series only works at one value of x, which is the x where you're centered around. But sometimes you can go away from that, plus or minus the same amount. So it's like margin of error in statistics. It's you have your mean, your sample mean, and then you go either side equally with your margin of error. So the same kind of thing applies here. There's this thing called the radius of convergence, and that's the distance away from the center point where the power series converges. Sometimes that radius can be infinity, and therefore if you have a Maclaurin series that's centered at x equals 0 and the radius of convergence is a infinity, then it means that the series works for all values of x. But a lot of times it's not. Again, if you go back to that sheet that we handed out, you'll notice some of them are a lot of them are plus or minus 1. So they work at x equals, say, 1. This might be the case for this square root function, or the square root function that I mentioned here, or well, in the previous section. That may only be good plus or minus 1. I don't know, but we could figure it out once we learn how to do this. Okay, so let's read what it says. For a power series centered at C, precisely one of the following is true. The series converges only at C, so that was the worst case scenario. Second case is there exists a real number greater than 0 such that the series converges absolutely for the absolute value of x minus c being less than r, and diverges for the absolute value of x minus c is greater than r. So what that's saying is that the radius of convergence can be finite, and it always goes plus or minus the same amount. And if you stay within that plus or minus, then it converges for all values of x within that interval. But if you go outside of that interval, go more than plus or minus the radius of convergence, then it diverges. And the third choice is that the series converges absolutely for all values of x. So the sine, the cosine, the e to the x, those are examples of power series which converge for all values of x. Now, one thing you may have not noticed, but it says that it converges absolutely up to r, and it diverges greater than r. So the question is, what happens at r? And we have to look at that a lot of times we have to use one of the other tests besides the ratio test to answer the endpoint questions. So that's sometimes one side works and the other side doesn't work. So it might go, say if it's centered around 0 with plus or minus 1, it might converge at -1 but diverge at +1. It might diverge at both positive and -1. So you don't know until you actually do the test. So the number r is the radius of convergence to the power series. If the series only converges at r, the radius of convergence is 0. If the series converges for all x, the radius of convergence is infinity. The set of all values of x for which the power series converges is the integral of the convergence of the power series. What does that mean? I think it just means that, I don't think it's integral as I think it just means includes. Yeah, I don't know what I hadn't noticed that. What does that mean? Interval. That's what it is, because it doesn't make any sense with integral. So interval, you're probably right. I just wrote it down wrong. Yep, you're right. Thank you. That makes a lot more sense now. Interval of convergence, not integral of convergence. I'm like, what? Never heard of that before. No wonder, because I made it up. Okay, you don't need to write all this stuff down. We're just going to, so we're just going to do it. So these are power series that I don't know what they, these power series don't have to be a Taylor series or Maclaurin series. They can just be any kind of series that somebody comes up with that has an infinite number of terms, and it involves x. So we're basically trying to figure out for which values of x does this series converge. And you could, one way would be to try every value of x and do the whatever appropriate test is, but that's that would take you forever, literally, right? So what we do, so we're going to use the ratio test. To determine the interval of, the radius, I guess, the radius, and then the interval of convergence, not integral. Okay, so the ratio test says take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. In this case, we actually don't use a sub n because that would be just the part that doesn't involve x. We actually do we call it u. So it's going to be u sub n plus 1 over u sub n, where that includes all the terms in this part. So for our case, u sub n is just 2x to the n divided by n squared. And u sub n plus 1 is 2 times n plus 1, 2x. 2x to the n plus 1 divided by n plus 1 quantity squared. So you just substitute n plus 1 for n in the previous expression. And then you take the limit as n goes to infinity of that ratio. So it's going to be 2x to the n plus 1 divided by n plus 1 squared divided by, so that's u sub n plus 1, 2x to the n divided by n squared. And in the ratio test, what we do is we take the reciprocal of the denominator. So we change division into multiplication. So you're going to have 2x to the n plus 1 divided by n plus 1 squared times n squared divided by 2x to the n. So I just take that, take the reciprocal. And then I'm going to group the terms that look similar. You could probably go straight from here to here if you feel comfortable about it. So we're going to have n squared divided by n plus 1 squared, 2x to the n plus 1 divided by 2x to the n. And remember, for this thing to converge, it has to be less than 1. So that's so the ratio test says for a series to converge that the ratio of a sub n plus 1 over a sub n, absolute value, as n goes to infinity is less than 1. So we're doing the same thing here, except we're using u as the symbol. So the kinds of terms that you're going to end up with is exponential type terms where the exponent is n, or n plus 1, which we can simplify using the properties of exponents. You end up with terms that involve n. A lot of times that ratio ends up being 1, which is what's going to happen in this case. When n goes to infinity, you're going to have n squared, and if you multiply this out, you'll have n squared plus 2n plus 1. And the lower order terms become insignificant, or you can take the ratio of the leading coefficients. So these terms usually end up canceling out and just becoming 1 when n gets very big. You also have factorials a lot of times, so you might have n plus 1 factorial over n factorial, which we know how to simplify as well. Sometimes you have, those are the main ones. I'm trying to think, the other one might be where n is the base, which, but I don't remember any, I can't remember any of those right now. Okay, so all we can do in this case is simplify the second term. We can go ahead and multiply out the first term, so we have n squared plus 2n plus 1. And here you just end up with 2x. So this first term goes to 1. So what we get is that as you take the limit as n goes to infinity, this goes to 1. This doesn't change because it doesn't involve n. So you get 2x, absolute value of 2x has to be less than 1. Now, how do you handle the absolute value? Well, the way this works is this is the same as that. So when you have an absolute value, have an inequality, you can make this into a 3-part inequality. And you take plus or minus whatever that is. So if this is 2, you go from -2 to +2. If this was 7, you go from -7 to +7. And I'll demonstrate how that works. So now, once you've got this, you can solve for x. So we divide everything by 2, so you get -1/2 there, and you'd get +1/2 there. So this is my interval of convergence. Actually, I never did the radius of convergence. The radius would be a half. Okay, so if I solve for x, if I said, if I divided by 2 like that, I'd get that. So this is my radius. It's just the value that you go plus or minus around the center point, which in this case is 0. This is my interval of convergence. Well, not quite, because I haven't answered the endpoints. So because we just have an inequality here, we don't have one that involves an equals. We don't know what happens when x equals -1/2 or x equals +1/2. So the first part involves a ratio test. You usually end up with something like that, where you have the absolute value of something is less than something, and then you rewrite it in that form so that it ends up being an interval. And you can kind of see, if I put x equals 0 in there, I'll have 2 times 0, which is 0, absolute value of 0, which is less than 1. If I put in -1/4, I'll have 2 times -1/4, which is -1/2. Take the absolute value of that, that's +1/2. So that works. If I go on the other side, +1/4, I'll put that in there. 2 times 1/4 is 1/2. The absolute value of 1/2 is 1/2. And so that's the right thing to do. I don't know what, there's probably some better way of explaining it, but it's true. So endpoints. Because the ratio test is inconclusive at when it equals this, when it's equal to 1. So the endpoints are going to be when x equals -1/2 and when x equals 1/2. And so we go back to the original series, which I've forgotten what it is, 2x to the n over n squared. Okay. 2x to the n over n squared. Okay, so if we plug in 1/2, we'll get, and this is from n equals 0, 1. Okay, so we go from n equals 1 to infinity. So we plug in x, whatever the endpoint values are, determine from our interval of convergence. So we'll have 2 times negative 1/2 raised to the n power divided by n squared. And over here, we'll have two times positive 1/2 raised to the n power divided by n squared. And if we simplify that down, we'll get negative 1 to the n divided by n squared. And over here, we'll get positive 1 to the n over n squared, which is just equal to 1 over n squared. So, and that happens a lot. One of the endpoints gives you an alternating series, and one of the endpoints gives you a non-alternating series. So where you have the negative part raised to some power. So this is an alternating series, and this is a p series. So you look at these series and use all the tests that whichever is appropriate. The ratio test is not appropriate because we already found that's inconclusive. So in this case, they both converge. This one converges because it's an alternating series, and the limit of 1 over n squared as n goes to infinity is 0, and a sub n plus 1 is always less than a sub n. Okay, that would be, and I'll write it out in just a second. This one is not an alternating series, so you can't use the alternating series test, but you can say it's a p series, and because p is greater than 1, this also converges. So let me write that out for you. So this is an alternating series where the limit as n goes to infinity of a sub n equals 0, and a sub n plus 1 is always less than a sub n. So it converges. And over here, this is a p series where p is greater than 1, so it converges. And so what we can do now is, after you evaluate the endpoints, we can expand our interval of convergence to include the endpoints. So now it becomes that. And that's your final answer right there. Okay. So in review here, so all power series are evaluated for convergence relative to the radius of convergence and the interval of convergence by using the ratio test. You'll end up with some value here. Sometimes it's good for all values of x. That means it's going to be converge for all values of x. Sometimes, like this, it's going to be converge for a range of x values. The ratio test tells you the range, but it doesn't tell you what happens at the endpoints. So you have to take the values of the endpoints, plug them back into the original power series, plug in x equals whatever those endpoints are to come up with the series that don't involve x, and then you use the appropriate test to see whether the endpoints converge. And you're like, well, where might this not converge? Well, let's say if I wasn't dividing by n squared, but I was dividing by n. If my original series was divided by n instead of n squared, the alternating series part would converge, but the non-alternating part would not converge because p would be equal to 1. So there are cases where it does converge on one side and not on the other. Okay, so well, here's, so speaking of that kind of problem, here it is. So let's see how this compares. So it's very similar. You don't have the 2 in there. But the denominator is n instead of n squared. And you have this alternating part. So there's a couple of things different with this one compared to the previous one. So how do you handle this negative thing? So let's just go through the whole process again. So u sub n is -1 to the n. You do include the -1 part here. And then u sub n plus 1 is -1 to the n plus 1, x to the n plus 1 divided by n plus 1. And then you take the limit as n goes to infinity of the absolute value of u sub n plus 1 divided by u sub n like that, and that has to be less than 1 for convergence. So why don't you go ahead and simplify that. Take the reciprocal, group the terms together. You should be able to simplify the exponential part here. This one you can't, the n's don't simplify, and you should be able to simplify the -1 to the n powers. Those are just like these. Here the base is -1, here the base is x. And really, when you simplify it, you'll find out, what do you do with the -1 that's kind of sitting there? Well, because you're taking the absolute value, you pretty much can drop that. The -1 really doesn't impact the interval of convergence. It will impact when you evaluate the endpoints. It will have some impact on it. So I think if our original series was just x to the n over n versus -1 to the n times x to the n, you get different results for those two cases. So there you go. So -1 to the n plus 1 over -1 to the n is just -1 to the first power. These don't get simplified. And x to the n plus 1 over x to the n is x to the first power. This goes to 1 as n goes to infinity. This gets dropped because it's an absolute value. So you just end up with the absolute value of x has to be less than 1, or the value of x has to be between -1 and +1. So that's my initial interval of convergence, then you have to evaluate the endpoints. So the endpoints are x equals -1, x equals 1. The original series was the summation from n equals 1 to infinity of -1 to the n times x to the n divided by n, I think. -1 to the x, okay. So if you put -1 in, you'll get -1 to the n times -1 to the n divided by n. And if you put in +1, you'll get the summation from n equals 1 to infinity of -1 to the n times 1 to the n divided by n. So here we have -1 to the 2n divided by n. So we have the same base. You add the exponents when you multiply them together. So n plus n is 2n. Over here we have -1 to the n times 1 to the n. Well, 1 to the n is 1. So we just end up with -1 to the n times 1 over n. But -1 to the 2n, anytime you have n is always an integer. So this is always going to be even. So we can say since 2n is even, -1 to the 2n is positive. Not just positive. So we can reduce this down, simplify it down to 1 over n. And this one is -1 to the n to the 1 over n. So this side, it's a p-series with p equal to 1. This diverges. This is an alternating series where the limit of a sub n as a sub n goes to infinity is 0, and a sub n plus 1 is always less than a sub n. It's always greater than 0. So because of that, that's going to converge. I'm just going to write it out. I'm not going to write out the details here, but we're going to say diverge p-series p less than or equal to 1. Over here, converge. It's an alternating series. And it converges because the limit as n goes to infinity of a sub n equals 0, and a sub n plus 1 is going to be less than a sub n. So those are the requirements. Those are the convergence criteria. This is the kind of series. That's the result. This is the kind of series. This is the convergence criteria. That's the result. So we can go back over here. And so when x equals -1, it diverges. So that still remains an inequality. But at x equals 1, it converges. So that becomes an equality. So that's both, this has a radius of convergence of 1, but the interval of convergence is greater than -1, but less than or equal to +1. Like I said, if the original series had not had this alternating part, probably it would have diverged on both ends, I guess, I would think. My guess is that. So on Monday, what we'll do is, I'm not going to hand it out today because I'm going to have, this. Well, actually, I'm going to hand it out today because I don't know whether those band people will be in on Monday, so I might as well hand it out today. So this is some problems that we'll go through, and there's 4 of them. So we'll get a lot of practice at doing intervals of convert. Well, that's not exactly true. 3 out of the 4 are intervals of convergence. The fourth one is just writing something as an infinite series. So not yet. I think we said next Monday or something like that, or Tuesday. Wasn't it Tuesday? I think because I was giving the band people some extra time. Actually, yes. Yep. Oh, sorry. Yeah, that's right. Actually, one more thing I'm gonna show you before we quit for today is so the infinite series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So if I asked you to evaluate what is e to the I pi, so is that what I want to do? Does anybody know what that's equal to? -1, right? Okay, it is. So why is that? So if you were to plug this into the infinite series, then yeah, I know why it is. It might take longer than 7 minutes, but let's just try it anyway. So what you can do is you can plug that into the infinite series. So you'd have 1 plus I pi plus I pi squared divided by 2 factorial plus I pi cubed over 3 factorial plus dot 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 dot. Okay. So then you can, if you here you have I squared, which is -1, so that'll be negative. So it'll be -1 times pi squared over 2 factorial. And then you have plus I cubed is -I, so you get, wait a second, did I do it wrong? I cubed is, yeah, -I. Because I squared is -1, so then you have -1 times I, which is -I. So you get negative I pi cubed over 3 factorial. And you can kind of follow the pattern along. Now, if you do the same thing for the sine of, you can do the same thing for sine of I times pi. The infinite series for the sine is equal to, the sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And yeah, I don't have to think about this. Anyway, ultimately, it's not falling out exactly. I've done this before and I can't remember exactly. Let me just sit back here and think about this for a minute. E to the I pi is -1. Anyway, you can prove this using infinite series. The guy who came up with this originally, Euler, or Gauss, one of those guys, I think it was Euler, he just kind of figured it out, but I think, if I remember correctly, what you find out is that the there's another thing that you can do. That is correct. Am I writing that out right? I haven't done this for a while. It's called Gauss's theorem, I think. Gauss's theorem. Let's see what it says here. That's not the one I was thinking of. It's called Gauss's something or other. What's it called? It's Euler's. It actually is Euler's identity. Thank you. I knew it was one of those guys. Euler's identity. Yeah, so e to the I pi plus 1 equals 0, which is the same thing as we were saying. There's also another thing that, so I'll look at this and there's another one that is used a lot, is that e to the I theta is equal to the cosine of theta plus I sine theta. So, and this relationship. I mean, you think of e to an a imaginary number times an angle theta in radians, and then you start to think, is all this just playing around with stuff and it doesn't really have any usefulness? But it turns out this actually has a lot of usefulness. Actually, in physics, when we were dealing with capacitor, inductor, resistor circuits, and we looked at phase angles, and you can solve, even though you can solve real differential equations using imaginary arithmetic, and then when you get to the end, you take the real part of the solution, gives you the real answer. And so there's a lot of good stuff out there that use some things that you might initially look at and think is a little esoteric. So if you take differential equations, we actually use this conversion between, because you can see here, the real part of this expression, well, you've got a real part and an imaginary part. So, and what you can do is you can just add and subtract angles like you do around a circle to relate different vectors, kind of like a vector. This is like the x-axis, and this is the y-axis, and this would give you a vector related to the angle relative to the x-axis. But yeah, it's not coming immediately to me, so it'll take me about 5 minutes to figure it out. But